Howdy y'all, and welcome back to the channel. One of the perks of my job here as the Deputy Director of George Mason Observatory is that I get to host the Evening Under the Stars. Evening Under the Stars is a public event series we have every semester, where in the first hour, we have a public talk given by someone in the astronomical community, be it a scientist, an astronomer, an engineer, a journalist, or even a citizen scientist. This video will be highlighting the talk given by Dr. Stefanie Milam back in November 15th. The talk is entitled New Eyes on Our Solar System with the James Webb Space Telescope. Dr. Milam is the Deputy Director for Planetary Science of JWST. So without further ado, I will cut over to her talk, and I hope you enjoy it. Thank you.
Can you hear me online? Yes, okay, great. All right, I apologize for the delay. I will try to make up for time and keep you guys on schedule. I'm Stefanie Milam. I work at NASA's Goddard Space Flight Center, so just down the road. Depending on traffic, it's about an hour, two, whatever. But that's okay. It was worth the drive, and I'm happy to see faces, and thanks to those of you online as well for joining me. I'm the Deputy Project Scientist for Planetary Science. So what that means is I work on the James Webb Space Telescope to ensure that we could observe objects in our own solar system. So I'm going to give you a couple of the highlights of things that we've been doing, how we've achieved doing this with the James Webb Space Telescope, and as opposed to looking at the first galaxies and planets around other stars, and a couple of fun highlights and things to come. So we'll get started. I can get started. And hopefully they can hear that online. Christmas Day, 2021.
Liftoff from a tropical rainforest to the edge of time itself, James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight, to hit program reported. And let's go down to the floor control system.
One of the most terrifying days of my life, a mission that I'd worked over a decade on. We spent years and years and years assembling this telescope, carefully testing it to make sure everything would work, multiple budget extensions and timeline extensions, and then we stuck it on top of a rocket and then ignited that rocket. That's pretty terrifying. But everything was absolutely nominal, which I think is totally underselling what it actually was. This was a beautiful launch. It was so perfect, in fact, that you couldn't see the discrepancy from the predicted launch trajectory compared to what we actually did. The errors were so small, it was spot on. We had a perfect trajectory that actually enabled us to detach from the rocket itself, put us into a position where we could make our first burn of fuel to push us off towards the second Lagrange point. And we conserved enough fuel that we now know that we have about a 20-year mission lifetime. So this was incredibly successful. It was a very emotional day for a lot of people. Not to mention, we actually got to see the spacecraft detach. It was Webb's last view of Earth.
We do have confirmation of observatory separation. The James Webb Space Telescope, amidst applause here in the Mission Control Center, now taking its first steps in pursuit of cosmological discovery.
This was tremendous in of itself. Just that image in and of itself is something that you couldn't have imagined. But then we got to see the very first deployment of the James Webb Space Telescope.
appropriately enough, as we marvel on this view from the upper stage camera, this will be humanity's last view of the James Webb Space Telescope as it moves to its workplace about 1 million miles away from Earth.
So watching our solar array deploy was absolutely unexpected. This meant that our trajectory again was so perfect. We were expecting to have to kind of fix ourselves from tumbling after detachment, and we didn't have to. And as soon as our sensors felt that we were in the right position at the right place, it automatically deployed their first deployment, which was the solar array, so that we could collect power and get off of batteries. This was amazing. It was phenomenal. And it was the first of over 100 deployments that we had to go through. We were on our journey at that point to go 1 million miles away from Earth. We were going to the second Lagrange point. So we orbit around the sun with the Earth. We are always on the anti-sunward side of the Earth. We're in an orbit around the second Lagrange point. So it's a gravitational saddle point. It's not an actual fixed gravitational point. So having our launch actually push us into L2 without over pushing it, you can imagine trying to drop a marble into a well and making sure the marble doesn't come out the other side. You want it to kind of just sit just perfectly so that it rests in that well. And we did that perfectly. And that's an actually very large orbit around L2. It's almost the same distance from the Earth to L2. It's a very large elliptical orbit. But it gives us access to the sun 24 hours a day, and also access to the Earth for communications. So we have a rather small solar panel for power, but that's because we have access to the sun, and we have communications routinely. The moon never inhibits the solar array or the communication with the Earth. So we're constantly in communication as needed. On our journey, we finished the rest of our deployments. It took a couple of weeks. It was pretty terrifying. Hopefully you watched along and appreciated how absolutely exhausting it was to go through this as far as the project goes and the whole world. But we started with, deploying our sunshade so that we could start cooling our observatory as quickly as possible. Though everything was done in a very systematic way, we didn't want to cool things down too fast because you don't want ice condensing on your optics or your instruments. But you also don't want to cool it down too slow because we have a timeline and we wanted to get ready for science. So things were moving at a very rigorous pace, but also at a very controlled manner. So this was a very complex series of events that took a couple of weeks, and everything went beautifully, and we had a fully deployed telescope. So we have a funny looking observatory, and that's basically because we want to keep a nice cold telescope. We have an infrared observatory. So that means that the mirror and the science instruments always are away from the sun. So as I said, we're orbiting around the sun with the Earth. And because of this funny shape, that gives us a weird trajectory of the sky that we actually can see. So we can't see midnight because we can't actually tilt the telescope enough so that the mirror points directly at midnight for us. So we see sort of an annulus. It's like a donut of the sky at any given time because we can move sort of in a circle, but we can't tilt all the way up and all the way down. So that's why we do have sort of a boat-like structure. So it gives us a little bit of that pitch, but we don't get a full pitch to actually see the full midnight sky. But this does give us access to the full sky about twice a year. So it's pretty fantastic. I'm sorry, you guys are seeing, I don't know how to make that go away. Is there a way to hide it? Yeah.
You can move your cursor.
Oh, look at that. Go away. Yeah. 2 PhDs to figure this out. All right, back onto this so I can. Okay, so this is just a quick comparison and snapshot of what we have compared to our predecessor, the Hubble Space Telescope. It gives you a sense of scale and size, and I'm also going to give you a handful of facts. So JWST, the sun shield's about the size of a tennis court. So it would fill this entire room, and it stands about 3 stories high, whereas Hubble in its launch configuration is about the size of a giant bus. You can think of a commercial bus. The mirror of Hubble is only 2.4 meters, whereas JWST has a diameter of 6.5 meters. For scale, I'm just over 1 segment high. And that's not saying a lot because I'm a pretty short person. So, but anyways, we're competing with a 31-year mission lifetime of the Hubble Space Telescope with multiple servicing missions. But you will notice that there is a mass of over 12,000 kilograms or 12,000 grams of for the mass of Hubble, and that was its launch weight. And JWST is actually half of that. That's because we had to send it a lot further away, and we have a much larger observatory. So getting something that large, that much further away, took quite a bit of innovation and engineering challenge just to ensure that we could get this observatory that far away, something so big. And we passively cool the telescope, the mirror, and the instruments by sitting in the shade. So just think of passively as just sitting in the shade. And as I said, we are now on our journey for a 20-year science mission lifetime. So in comparison to Hubble as well, we have to think about what the James Webb Space Telescope does that's different or complementary to what Hubble does. So it's an infrared telescope, which is also why it has a gold mirror and not an aluminized mirror. Gold is very reflective in the infrared, and I can attest to that with my own gold mirror now. So it is absolutely ideal for operating at the wavelengths that the James Webb Space Telescope operates at. So you see Hubble is mostly a UV visible near infrared observatory. We also had another predecessor telescope called the Spitzer Space Telescope, which was another infrared observatory, but it operated at quite a bit longer wavelengths, and it was a very small telescope. The primary mirror of Spitzer is about the size of the secondary mirror of the JWST. So it gives you a sense of scale, just to understand. So why infrared? Mostly because this is an astrophysics mission, and it was designed to study the first stars and galaxies of the universe. And so what you can imagine is these galaxies that are extremely far, far away. The universe is expanding. These galaxies are moving away from each other. And as they do, they also stretch and pull the light away from each other as well. And so that light is also being stretched and pulled away from ourselves. And this is why light then gets shifted to longer and longer wavelengths, because we're actually stretching that light out. And so this is what's known as cosmological redshift. So we study these populations of galaxies at different times and distances across the universe. And this gives us a lot of information about, how galaxies formed, how our universe formed, how galaxies actually evolve. And as we've looked further and further back towards the beginning of the universe, we notice that galaxies have these fantastic, beautiful structures that we can actually see with telescopes such as those here on the roof. But as we look further and further back in time, we notice that they start losing structure. The colors change, and we don't really understand what's going on because with the resolution of Hubble, things just turned into red fuzzy blobs. So with JWST, we're hoping to start resolving some of those red fuzzy blobs and understand how these things evolve and get processed with time. But galaxies, schmalaxies, whatever. I'm a planetary scientist, so I care about things that are a little bit closer to home. More specifically, how stars and planets actually form, and what that teaches us about the evolution of our own solar system. So at infrared wavelengths, we can actually see through large clouds of gas and dust that are across the universe. A lot of these are in our galaxies, and they're known as star-forming regions. So at visible lights, these clouds actually obscure light the same way clouds in our own sky do. On a cloudy day, you can't see the sun, you can't see anything in the sky, and on a cloudy night, you can't see stars, etc. Same thing goes with our own galaxy. We cannot see through these galaxies or through these clouds at visible light. But when you start going to longer and longer wavelengths, we turn on our night vision goggles and we can start seeing inside of these clouds. And that's where we can study how new stars and planetary systems have actually formed. And if you go to even longer wavelengths, you can start understanding the dynamics and the chemistry of these regions, which is something we haven't had a whole lot of access to, especially with the beautiful resolution that we get with the James Webb Space Telescope. So we've opened up a whole new can of worms and science that's enabled by this observatory. And of course, there's planets around other stars and the whole hunt for Earth 2.0. This is actually Earth's spectrum at wavelengths that JWST operates at. And what we were hoping to achieve at some point in our lives, or maybe the next generation, or maybe, with Astro 2020, a couple of generations away, looking for Earth 2.0, and we want to see a spectrum that looks like Earth's atmosphere. So we want a habitable world that has oceans, liquid water on the surface with some terrestrial and terraform capability, also potentially a habitable world and potentially life. So when you look at the spectrum, it doesn't say anything about life specifically, but what it does tell you is that the chemistry is different. It's not in equilibrium. And so that's sort of what the high level profile science case is for studying planets with JWST. We want to see something that is different. We don't know why it's different. It could be due to geology. It can be due to large impact events. It can be due to a moon collision, with a planet. Our Earth's history has changed its atmosphere so many different times. And what life has contributed to the atmosphere has been just a blink of an eye. So we just want to find something that's different. And that's going to give us a short list for the next telescope and the next telescope, something that we can really hone in and study a little bit more in detail as we get more and more sophisticated and clever about how to observe these planets. So it took us a while to get all the instruments up and running. We had to focus all 18 segments of the mirror. And sure enough, as soon as we did, this is what all 4 of our science instruments, including our fine guiding sensor, looked like once we got the telescope focused. And I'm just going to give you a hint that it's really, really, really good. So Spitzer, our predecessor infrared telescope, shown here on the left, compared to JWST with our first focus instrument at similar wavelengths. This was emotional for everybody on the project and people around the world. This meant that we actually were able to do the things that we set out to do. And we knew that the science was going to be fantastic, and we knew the images were going to be amazing, and the spectra was going to follow. So we started off with a bang. And then we got our first observations in. Now, I was one of the few fortunate people that got to see these images before anybody else in the world. I review material that goes out to the public from JWST and NASA, and they came across my desk, and I had to sit there and take a breath, blow my nose a couple of times, wipe my eyes. I was so emotional and just torn apart with how beautiful and spectacular these images were. So I'm just going to step through a few of them, give you some insight and a little bit of detail, but if I cry, it's your fault. Okay, so we're going to start with the first deep field. This is Webb's first deep field, but this is not Webb's image. This is the Hubble Space Telescope version of this deep field. This image took a couple of weeks with the Hubble Space Telescope. Just for some perspective, this image, the whole size of it, is about the size of a grain of sand. If you stuck it on the end of your finger and put it out at arm's length, that is the amount of sky that we're covering with the entire image. Weeks of data to acquire this fantastic image with the Hubble Space Telescope. JWST, in only 8 hours, already surpassed the capability of the Hubble Space Telescope. Just going back, notice how many new dots, how many new sparkles, how much more glitter actually appears when the JWST image comes up. Not only the more dots, but the resolution, the clarity. If you haven't done it, download these images and just zoom in and zoom in and zoom in and zoom in. Zoom into your favorite ones. You're going to see something fantastic, I promise. Every single time I've looked at this image, and especially on the giant hyperwalls that we have, it's mind-blowing, the capability that we have. And this is only 8 hours. Hubble Ultra Deep Field was hundreds of hours. We are already achieving and surpassing the capability of Hubble Space Telescope in just blinks of an eye with the James Webb Space Telescope mission. This is rewriting the textbooks for us. Some of the fun features about this image are we see these sort of melty, blobby, streaky looking things. They almost look like Dali kind of paintings. These are galaxies that are being pulled and stretched because they're actually distant galaxies. So what you have is a series of, I don't know if I can see, okay, 5 massive galaxies in the foreground. And they're so massive, they're actually distorting the light from the images or the objects behind them. And those are being swept and pulled around. And so you get these fantastic distortions and stretching. We can actually see whether or not they're the same galaxy by studying their spectra. And a couple of them are, but not all of them. Some of them are actually unique objects. But this is a fantastic way and something that Einstein actually predicted. We've seen this with other observatories. You can see this in the Hubble images as well. But the clarity, again, and the spectroscopy that we get with JWST is only more revealing and more powerful. Planetary nebula. So this is the Southern Ring Nebula. When I was a graduate student, I was studying evolved stars. And I looked at all of Hubble's planetary nebula images. I had this fantastic poster in my office. And I was like, I'm so cool because I have a poster of Hubble images and I study these objects. And I thought there was nothing more spectacular. And then I saw JWST's version. So this is the near infrared version of the Ring Nebula. What you can already see is the incredible amount of structure that's revealed. You actually see the arcs of material that have been lost through episodic mass loss from the star. So this is a dying star. So what's happening is it's blowing off all of its stellar material as it's dying and pushing it away, revealing that hot inner star, which is then illuminating the rest of that gas and dust as it's being ejected. But if you go to longer wavelengths, so this is the mid-infrared version, you actually see that it's not one star, but it's 2. You can see 2 distinct stars. This is a binary system, which we know from spectroscopy before the JWST images, but this is the first time it's been resolved in an image. And so you have a star on the left, which is the red one, that is the dying one. And then the star on the right is a white one, bluish white one. That is its secondary star, which is actually a very bright hot star, which is helping illuminate this gas and dust that's being ejected from the dying star. Stephan's quintet is one of my favorite images. This is absolutely fantastic image. So there's 5 galaxies in this image. It's actually one of our largest images that we took for our first images that were released. The 4 on the right are actually all in close proximity and interacting with each other. The one on the left is a photobomb. It's actually tens of thousands of light years closer to us than the other ones. But it actually makes a beautiful apparition, and we get to see a whole different level of galaxy evolution and interactions. So there's all kinds of things that are revealed, including the active galactic nuclei, which when we go to the JWST version of this, again, all the more glitter in the background that is revealed, showing you the capability of JWST, all the distant galaxies, which are everywhere. They're in every image we look at. But also all the fantastic structure. Again, the active galactic nuclei up in this upper galaxy is actually highlighting and illuminating all of this gas and dust that's being pulled into that massive black hole. At longer wavelengths, it's even more beautiful. In the interest of time, I'm not going to go into details on all of these, but I could sit here for hours and tell you all the details that I love. The Cartwheel Galaxy is another example of colliding galaxies. So this is 2 galaxies that have actually collided a while ago and created this fantastic looking image. So again, this is the Hubble version compared to the JWST. All the structure, again, that's revealed, the level of detail, and don't forget the background galaxies that are revealed. So my favorite image that we released was of the Carina Nebula. But I wanted to give a little bit of perspective on this. So this is a fantastic image of the region. And I'm going to do a couple of zooms. They're all highlighted in the red boxes, just to give you an idea of how well we're doing. So this is sort of your fantastic ultimate clear sky, sort of your standard ground-based heavy-duty binoculars or, backyard telescope level image. Get a decent telescope and you can see structure of the Carina Nebula. And zooming in again and again, this is a large ground-based telescope. So this is Lucia Observatory. And finally, zooming in on that red square on the upper right, what we reveal with the James Webb Space Telescope. Now, when this image was revealed, I will tell you that the scientist that was leading these observations, we had to pry this image from his hands. He is passionate about star formation, and that is his science area. And he sat here and dug and dug and dug into this image. And we're like, you're not allowed to science the early release images. We're not allowed to science anything yet. We have to wait until everything becomes public and then we can science it. And he's like, but look. And look, we see star formation actually happening within our eyes. So these are fantastic zoom ins of this image. Again, if you haven't downloaded, if it's not your background of your computer screen or your phone, I don't know why you're sitting here and you don't get a JWST sticker. But if you zoom in and you zoom in and you zoom in, there's fantastic structure that's revealed, and so many things are happening that we have no idea of how or why it happens. We don't know how massive stars versus smaller stars are formed in the same region. We don't understand the interplay of how these are all new stars up here, these white glittery objects, which are so bright and radiative, they're actually destroying all this gas and dust. But all this gas and dust is also forming new stars within it itself. So there's a competition of that material on what's actually being destroyed and what's being eaten and consumed to make new stars. We have no idea how that balances out, how all these interactions work. These shock regions of new stars, protostars that are forming, so they're collecting all of their material, but they're so energetic as they're starting to collapse. They blast out a huge amount of energy, and we're seeing it actually collide with the gas within the cloud itself. And we see that in multiple series just across this whole region, which is a tiny little region. But this is absolutely amazing, and it only gets better. The Tarantula Nebula, it's another one of these fantastic star forming regions, and it's absolutely beautiful. Again, an extremely massive star that's just formed in the center there, and how it's competing with killing all the material around it versus the new stars that are being formed. And if we go to longer wavelength, seeing how that's dynamically interacting and exchanging with the molecular cloud material around it. And of course, we've been looking at planets around other stars, blah, 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 blah. So one of the ways we do that is through transit spectroscopy. This is our most sensitive technique that we have with the James Webb Space Telescope to study planets around other stars. So whenever a planet passes in front of its star, we watch the starlight dim. And if it has an atmosphere, we can actually see what the composition of that atmosphere is by tuning into different wavelengths or different fingerprints of different molecules and seeing how much that light dims for a given molecule. And this is called transit spectroscopy, and it's a technique we've been using for years now to study the atmospheres of planets around other stars. We also can do this in our own solar system. As a planetary scientist, I like to point that out. So this is the transit of Venus. We know Venus has a huge atmosphere. It's crazy rich. It's phenomenal chemistry. I challenge you to find the atmosphere in that picture. Now, if this was a transiting exoplanet, we would, without hesitation, with a blink of an eye with JWST, be able to tell you what the exact composition of the atmosphere of Venus was. That's how sensitive our telescope is. But with our own eyes, you cannot see that Venus has an atmosphere. But this is how we do it. This is what we do, or this is what those really smart people that study planets around other stars do. So we took our first attempt at something that was easy. WASP 96b is a huge, bigger than Jupiter sized planet, but it's far less dense than Jupiter, which means it has a big puffy atmosphere. So we knew it was going to be something easy to detect gas in. So we looked for water, knowing that it was going to be a nice hot atmosphere because it's really, really close to its star. And lo and behold, we have water on a planet, or at least in the atmosphere. The surprising result from the spectrum is that the water signals aren't as intense as we thought they were going to be. So the peaks and the valleys of the spectrum, we expected to be, sort of 2 or 3 times bigger. But because they're not, means that there's some sort of something happening in the atmosphere of this planet, clouds or other dynamic effects that are actually causing things to look a little different. So voila, water on a planet. This was also the first time we'd had a spectrum from a planet of another star that was longer than about 1.7 microns. So we're finally getting into the JWST fun science regime. And of course, we want to know if there's something more than water, because yeah, water's even on Mars. Who cares about water? So a team actually was able to detect carbon dioxide. So this is step number 1 for finding some of those key ingredients and interesting chemistry in planets around other stars. We also want to actually image planets around other stars, and we do that with a technique called coronagraphy. So this is where you basically block the starlight so that you can see fainter objects around that star. So this is a simple technique. I don't know why it's not playing. Where we basically occult the star and the fainter objects are then revealed. And lo and behold, we've done this with JWST. Voila, there are planets that we have directly imaged at multiple wavelengths. I'm not going to go into all the details of this because I am not an exoplanet scientist. Ask the gentleman in the back of the room. But I will say, the only way we know anything about what we're seeing in these spectra or in these images around planets around other stars is to put them into context. And the best context that we have is comparing them to planets that we know. And those planets happen to be those that are really close to us, like our own solar system. But we know that our own solar system is extremely different than everything else that we've been able to observe. So what you're seeing here is these dashed lines show the orbits of the planets in our own solar system. Even these out here, oops, sorry, wrong screen. Even these out here and out here, these are still our own planets in our own solar system. Whereas these are all the planets that we found around other stars, and you can see that their orbits tend to be a lot tighter, a lot smaller, and the planets themselves actually vary in size from pretty big to pretty small. But we only have one way to compare them, and the best way to do it is with our own solar system. So JWST is actually studying objects in our own solar system, and that was why I was hired to work on this project, was to make sure we could actually study things that were a little bit closer to home. This is really important because there's a lot to be said about solar system science. It's something that you've learned from grade school. Everybody knows what Mars is. Everybody knows what Saturn is. So the public outreach, the education, as well as the science itself is something tremendous that we gain by doing objects in our own solar system. It's also hard. And we also don't have missions to every planet in our solar system, and we won't have missions to every planet in our solar system in the next decade, the next 2 decades. We won't have missions to every comet, to every asteroid, to every impact event. There are things that we just need remote sensing to do. And we had to make sure that JWST would be contributing to that science, answering the questions that we have for our own solar system. But because we have this funny boat-like shape, that means we can't point towards the sun, the earth, or the moon. Also anything in our inner solar system. So that makes Mercury and Venus, the earth and the moon out of commission, and the sun. But we can see everything sort of Mars on outwards, but that includes things like asteroids, near-Earth asteroids, comets, interstellar objects, as they come into the JWST field of view. But that's not easy to do. So this is a telescope that was designed to detect the first stars and galaxies of the universe. So we're searching for the far, far aways. And that means we have to be able to point very, very precisely and stare for really long times and look for the things that are far, far away. Yeah, okay, that's exciting. But I want to point at Jupiter, this really big thing, this really hot thing in our own solar system. It's kind of next door. You can see it with your own eyes when you go outside. Let's point our really sensitive telescope at that big bright thing. And the project was like, you're absolutely crazy, Stefanie. And I was like, no, it's really important if we do this. We want to know what's going on with the Great Red Spot. We actually observe all of the planets in our solar system with large telescopes on the ground all the time. There's all kinds of things happening that we just can't explain, and we want to know more. Okay, we'll give you a shot. So with a lot of innovation, a lot of technique, and working with our instrument scientists and our engineers, we figured out how to do this. And this was really important because, yeah, Jupiter is really, 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 really bright, which means all of that bright light actually scatters across the whole instrument field of view. So we had to know how well we could actually study something that big and bright. So what we did during commissioning was we pointed at Jupiter. These are less than a minute integrations each. So even the GIF that you're seeing. And immediately we saw the images and we were like, oh my gosh, it's so beautiful. And this is just commissioning data. And again, you know, the project comes back to us and they're like, don't science this. You're not allowed to science this. This is engineering data. We're like, okay, it's not very pretty, but it's also amazing. We can see the rings of Jupiter. Oh my God. So what we wanted to do was study how much of that scattered light affected the rest of the instruments and what we could do scientifically around big bright objects. So in the mid-infrared, you can see the dramatic effect that this had. So this is Jupiter and some of its satellites with the MIRI, so the mid-infrared instrument. So it's really, really hot in thermal wavelengths. So that means that it saturates very, very quickly, which is why it's a big black dot. But what we did was we sort of took images with MIRI going further and further away from the planet to see how bad that scattered light was and how long it perpetuated across the field, and gave us some insight into how well we could do the science that we hoped to do. We let the scientists take over and they started doing their sciencing. And this is the first science image of Jupiter that was released. Again, fantastic resolution of the rings, small satellites, aurora, the Great Red Spot, storms, high latitude clouds, everything you can possibly imagine. This particular image shows you the high latitude clouds in a beautiful way. All these little hot pink speckles going across the planet are actually real. And those are clouds that are really, really high in the upper cloud deck, reacting with the energy from the sun, as well as Jupiter's dynamic atmosphere. But the brightest thing in the infrared sky is actually Mars. And we wanted to make sure we could actually observe Mars because everyone told me I couldn't. And so I set out to make sure that we absolutely could, and ta-da, job security. So you're seeing two different images in the near infrared wavelengths. We can't observe it in the mid infrared, it's way too bright. But we did actually saturate on one of these wavelengths, but we were expecting it, but we weren't totally saturated. And I can tell you that because you actually see this dip right here on the Hellas Basin. That means that we're actually seeing some contrast that's coming through, which means we're not fully saturated. So there's a lot of science coming out of these data, including the spectroscopy, where we're digging in to see what kind of organics that we've actually detected, not to mention, oh my gosh, there's water on Mars, as well as other molecules that we've been anticipating and have observed with ground-based facilities. But with those ground-based facilities, we didn't get the full disk at a time, and it took months and months and months to make maps like these on the left. With JWST, we can do the full disk in about 30 minutes. So we'll be able to do a lot more dynamic studies of Mars than what we've been able to do with other facilities. So I know time is getting tight, so I'm going to start jumping through things pretty quickly. Probably I'm going to get distracted, and I apologize, but I don't. So stick around if you're interested. Neptune. This was a first glimpse of Neptune, and the first thing you notice is rings. The rings of Neptune have not been observed with another observatory for 30 years. It was the Voyager flyby. Keck has been able to do it. It's been very, very challenging, and they weren't able to see all of the rings. So with JWST, we demonstrated it within a blink of an eye. This is not even an hour's worth of data. In fact, I think the image on the right is 900 seconds. And what you see is a beautiful, fantastic Triton that looks like a star. This is because it's mostly nitrogen. It's extremely reflective at these wavelengths. And Neptune looks not blue like we know Neptune to be. And that's because the methane in the atmosphere is actually really, really dense and really, really thick. So it's absorbing all of that infrared light at those wavelengths. So the only highlights you see are these tiny little clouds that pop up. And these are really, really bright methane clouds. But again, all types of fantastic science already coming out of these images. Not to mention there's galaxies everywhere. Get these galaxies out of my data. But it's fantastic and it absolutely is brilliant. This is a brilliant apparition. More science to come though. We are going to be observing the ice giants with the mid-infrared instrument and doing some spectroscopy, which is something we haven't been able to do with the resolution or capability that JWST has ever. And why do we care about different wavelengths? Well, it helps us probe different areas of the atmosphere of a planet. So this image on the right is showing you how different wavelengths actually tell us about the chemistry that's happening in the atmosphere close to what we would think of as a surface, a troposphere or a haze layer. And then as you get up further and further where that gas becomes a little bit more diffuse and radiation from the sun starts playing around with those molecules, you get some photochemistry happening, and we can actually see that with different wavelengths of light, JWST being the most sensitive to those upper atmosphere sort of chemical effects. I couldn't tell you anything without talking about interstellar objects. We now know there are two. There's probably a lot more, but we've only found two that look extremely different from one another. One is Oumuamua, the AKA alien spacecraft, asteroidal object, and the second one is Borisov, which looks like a comet. These things fly through the sky, they're extremely fast, and that's how we know that they're interstellar, is because of their trajectory and their speed. Which means we have to actually make JWST track an object that's moving that fast. And so one of the tests that we also had to do was make the telescope slew across the sky and follow something as fast as an interstellar object. So we did a series of tests on different asteroids moving at different rates across the sky. And successfully, during commissioning, we're able to test up to 67 milliarc seconds per second, which is over 2 times faster than the speed limit that we had set out to do, which was 30. 30 is the fastest rate of motion that Mars actually has. So we already demonstrated that we can move really, really fast, but we then had another project at hand, and that was to observe the DART impact. So this is another NASA mission where we demonstrated that we could actually change the orbit of a satellite around another asteroid and move it by impacting a spacecraft into the side of it. And we wanted JWST to look at this, one, to help confirm the moving object's orbit, but also to see what was happening as far as the dust, if there was any chemistry, what that asteroid could have been made of, what the spacecraft was made of, who knows? So we wanted to take a look, but this meant we had to really push the speed limit of JWST up to over 100 milliarc seconds per second, which was quite challenging to do. But we were able to do so, and it was a fantastic success. So what you're seeing is sort of a video showing you just before the impact to just after the impact, about 5 hours after. And you see all kinds of dust and ejecta, which was also observed with Hubble at the same time. This was the first time JWST and Hubble observed the exact same thing in the sky at the exact same time. So this was really a fantastic demonstration and pushed the capability of JWST. So compared to some of the other images that you may have seen online, on social media, whatever your favorite platform is, we're getting the close-in view with these two observatories. They're really high resolution, they're big glass in the sky. And so you're getting the innards of the impact event. And so this was really a really cool demonstration, and a lot of science is coming out of this. Of course, there's lots of small bodies. We can't go to every single one of them and crash spacecraft into them. So we want to do sort of a whole statistical study of all of these small bodies. And we're working one object at a time, as JWST will do for the next 20 years. But we also can take advantage of some of these extragalactic, deep field, yada, yada, yada science, where they stare at the sky for hours and hours and hours trying to detect, galaxy far, far away. And that's because there's objects in our solar system that are moving across that field of view. So what you're seeing is actually a Hubble image where asteroids are streaking across the field. And that's what all these little arcs are. So 7 new asteroids were actually, 5 of these objects were actually new discoveries, new asteroids that have never been observed before, just by staring at this one deep field. And JWST is doing this routinely, day in, day out, because apparently people care about the first galaxies and stars and yada, yada, yada. But this is a whole different level of science that we plan to do with JWST. So I'm not going to go through all of the fun up and coming science because of time. I'm just going to skip through it real quick. I will say that we observed Saturn over the weekend and last night, and we got fantastic spectra. So stay tuned. We should have a press release coming out on that very soon. We've also been observing Titan. They got some fantastic images and spectra as well. That press release is sitting in my desk, hopefully to come out in the next few weeks. So stay tuned. Europa, ocean worlds in the solar system are an extremely hot topic. With JWST, we can actually get resolved imaging and spectroscopy across the surface of Europa, try to study the composition of plumes, see how they affect the surface of this icy world after plume activity. We'll be able to characterize what those plumes are made of, and or if they deposit sort of like lava on the surface, whether or not it changes that composition as well. Again, all of these are still happening. Enceladus observations just happened. Europa is coming, but stay tuned. Small bodies in the solar system, comets, interstellar objects, you name it, stay tuned. A whole survey of the outer solar system, the far, far aways in our own solar system. Stay tuned. And finally, today, we revealed that there is going to be the next year of science for JWST that is now available for you to propose to do. You tell us what you want to do scientifically, write your proposal, submit it by the end of January, and let the scientific community judge you in a competitive way and rank the proposals so that we understand who is going to be observing science with JWST next year. So the proposal call came out today. The deadline is the end of January. Please submit your proposals and think about all the amazing things you want to do with JWST. So with that, it's been a fantastic handful of months. I can't believe it's already almost Thanksgiving. It's been a long year, but it's been a really thrilling ride. I cannot believe the science that's already coming out of this observatory. Papers are coming out every single day. So peer review and science is happening in real time, and it's only going to get better. So thank you for your time, and I'll take questions.
Well, I'm going to take the prerogative to ask the first question.
Okay.
Privilege. Is there a question about the formation of the solar system, particularly the formation of these smaller bodies, that you would like and you think that JWST can answer?
Yes.
Okay.
Okay. So with the sensitivity of JWST, we can actually gain a lot better sense of what the size distribution is of small bodies across the solar system. So not only in the asteroid belt, but also in the Kuiper belt. So understanding that size distribution tells us a lot about how planetesimals, minor planets, even planets themselves actually start forming. We don't know if these are, things hitting each other and sticking together, or if it's really big things that collide and blow apart. And so there's some combination of that happens throughout the evolution of a planetary system, but we don't really understand. And we also don't understand what that limit is of things that actually stick versus burst apart. As we've explored the outer solar system, just initially with New Horizons, what we found is that some of these objects, even comets now, look like they're actually starting to just stick together. So understanding, is that a smaller body process, or is it something that maybe there was some other finer grain material that got lost during an impact and created these funny structures. But they seem to be adhering, and we want to understand what that actually looks like. And this means it gives us a little bit of information into how planets form, how planetesimals form, and how things start getting bigger and bigger and accreting. So that's something that I think JWST is actually going to really help reveal. And then as we get further and further into the next generation telescope, the Roman or JWST Observatory, we'll be surveying the sky and be able to get another sort of broader sense of what these objects look like. It won't have the sensitivity to get the same scales, but it'll tell us a little bit more about the distribution of them.
Okay.
So we're getting there. It's slow and steady wins the race.
As you said, job security.
Job security.
Are there any questions from our audience?
Ask a question. Okay.
Does James Webb have a primary mission goal in terms of what it wants to focus its research on?
So when it was first conceived, almost 30 years ago, that was to study the first stars and galaxies of the universe, which is why big, why infrared, etc. Since JWST was conceived and started on its journey to becoming an actual space telescope, we discovered planets around other stars. And we knew that we wanted to study planets around other stars with JWST. And it wasn't designed to do that, which is why it's kind of just scratching the surface of the capability of what we really want to do as far as exoplanet studies. But we're doing really, really well, and it's going to really help. It's already surpassing the capability of a lot of other facilities, but it's not going to detect Earth 2.0, right? So, but it's going to give us that short list of interesting things. So we have 4 major science themes. One is the first stars and galaxies, cosmic reionization, the birth of stars and planets, studying planets around other stars, including our own solar system. You get a sticker.
She wasn't kidding with the stickers.
Like I said, ask a question.
So you were mentioning how during development there were extensions and hiccups. I was wondering, was there any that like stood out, like any like major headaches or such and such that during its development that really delayed?
Since I've been on the project, so I started after the first major replan, which was in 2011. And since I had been working on the mission was when we started getting hardware at Goddard and started putting pieces together. The most major thing that besides COVID, that I experienced was when we were doing the vibration test and of the spacecraft and the sun shield, and nuts and bolts were lost. There was a pretty significant investigation on why that happened and how that happened. And basically it was just, lots of pieces, routine work with lots of different people. And the oversight was just kind of, it became monotonous. And the focus wasn't what it should have been, considering this wasn't a 1 in 100 orders of pick your favorite Air Force, whatever military spacecraft order. This is a one-off, extreme NASA, ESA, Canadian Space Agency. So it was found, which was fantastic, and that's why we do these tests, and something that provided a lot of information for us on how to complete the rest of, assembly and testing to get us ready for flight. It was significant. It was good that we found it. And if we hadn't, then we probably wouldn't, I wouldn't be standing here today showing you first images for sure. So you get sticker too.
I'm not sure exactly how to ask the question, but it's interesting. You've been on the project 10 years. It's been in conception 30. I'm not sure how long ago you got your degree, but and you're not an engineer, right? You're the planetary scientist. So what is, can you say just a little bit of what your role's been over 10 years in terms of, you didn't have the images to look at, but you're sort of, sounds like you're designing what it could look at or.
Yeah, exactly. So I have learned what my role is. When they first asked me to join the project, they're like, we want to make sure we can do stuff in the solar system. And I was like, so just point at stuff in the solar system. Like, how hard is it? I come from radio astronomy where, you know, we observe things in the rain and during the day, it doesn't really matter, right? So it was a challenge for me to learn what the challenges were. And then once I realized, oh my gosh, we have this giant boat that's extremely sensitive and floppy. And now I want to make it go like this across the sky so that we can observe Mars, which is also the brightest thing that it's ever going to look at. And oh my gosh, are we going to break the detectors? Are we going to, you know, burn them out or burn the optics or anything like that? And so it took a lot of work just figuring out what we could and could not do and why. So that's running simulations, that's providing science cases. So I want to study near Earth asteroids, which means I have to track faster than Mars. Why? What's the science you're going to gain for studying a near Earth asteroid with JWST? Why do we care? Is that something we can't do from the ground? Is that something that we're not already doing with the DART mission? What are we going to learn? And that's something that every astrophysics mission from here on out is now asking that question. Is there a science case? Is there a need to be able to track an interstellar object moving across the sky with this astrophysics telescope? Hubble was launched without that capability, and they had to figure it out on a whim when the Shoemaker-Levy impact hit the side of Jupiter. They didn't know how to track a solar system object at that point, so it was kind of pointing blind and hoping everything worked. The images aren't as clear as they could have been if they had tracking enabled and prepared to do those observations. So we wanted to make sure we were ready with JWST. And that's sort of what a lot of it was. It was also outreach to the community. The solar system science had sort of a bad taste in their mouth from past astrophysics observatories, where you have these extreme extragalactic scientists reviewing their science proposal saying, you can see Jupiter from my backyard with your own eyes. You do not need Hubble to look at Jupiter. And so they weren't getting a lot of time on telescopes. And I wanted to make sure that they knew that their science was significant and that they needed the time. And that way we could push and leverage that with the community, not only the planetary science community, but the astrophysics community, so that they understand the significance of what we do. Mm-hmm. Go ahead.
So you were talking about the 4 different things JWST is focusing on. What are you most excited about out of those 4 things, and what do you think will be easiest to observe and get more information?
So far, okay, I'll tell you what I'm most excited about, which is going to be surprising to everybody. But oh my gosh, did you not see Stefan's quintet? Those are 5 galaxies that are amazing. When I first saw them, I was like, I don't know why I don't study galaxies. I mean, planetary science is fantastic and it's beautiful and we're doing great things. But oh my gosh, those things are just amazing to me and they're just mind-blowing. The easiest is star formation. There's massive clouds all over our galaxy that we've imaged, we've looked at, we've studied, but this is a whole different level. And it doesn't matter what you do. I mean, you just point at it and you're going to discover something new. It's insane. It's crazy. But also anywhere we look at the sky, we see new galaxies. So it's not hard. It's amazing how easy it is to get amazing data. It's overwhelming. It's terrifying. It's job security. Are there questions online?
Oh, yeah. I should check those.
Not so far. They're still
No.
thinking.
Clear as mud. They don't get stickers though.
I have a question, maybe a naive one, on those images of Neptune, which are just phenomenal. I noticed at least two of the rings two of the moons almost seem to be producing the rings. Is that accurate? Is that correct?
Yes.
Okay.
A lot of the rings and most of the planets in our solar system are attributed to planets. I mean, to moons. So we know some of the rings around Saturn are created from the Enceladus plume. We can see that by characterizing that plume and then seeing what the rings are actually made of. And they did that with Cassini. And we'll be doing that with JWST. So we know that a lot of the rings are actually formed. But some of them also, we think, when we haven't attributed them to another known moon, means there's probably some moon there that we just haven't found yet.
Okay.
And so there are people that are working very hard to figure out what those moons are, if they exist, or whether or not they're just completely annihilated, and why.
Okay.
Great question.
To sort of extend on that question, does this mean that it's capabilities to say, characterize what's going on with Triton, see ongoing cryovolcanism?
Yeah, well, yeah. Triton's hard. You saw how bright it is. So there are observations that will be happening for Triton that are more specific, that are more science. That Neptune image was actually done as an outreach image. So the same as the first images that I was showing you. This was done to basically demonstrate JWST is awesome. But there is a science program to actually do those kinds of studies. And those observations have not happened yet. They'll happen in the spring. So stay tuned. Great question.
We have one here.
Well, is there a way we can get access to the PowerPoint to read it in the future?
Oh, boy. It is an extremely massive file because of the videos and the high resolution images. But if you have a platform you can post it on,
Yeah.
I can send it to you.
Yes, please do send it to me. We will find a platform.
Okay. All right.
We will definitely be posting that we're recording this. And so we will be posting this on the GMU Observatory YouTube channel. So you can definitely go back and rewatch it if you'd like. But if you provide the PowerPoints, I can certainly post them somewhere.
Okay.
So.
I might take all the future observation slides out just because they might not be as exciting. And I want you stealing my data. But almost everything that I have in here is publicly available. So if it's easier just to find it in the PowerPoint, I'm happy to share that. By all means, yeah.
I think we have another question.
I have a question. So you mentioned earlier that it actually went beyond its but you mentioned it went beyond its intended capabilities, right, in terms of speed. I was just wondering how thorough and how long the process is it to like simulate and test whether you should even go beyond that? Just because I understand like it's one of a kind.
Yeah, that's a great question. And I'm going to show, just so you get a sense of what I'm referring to. So we had to basically simulate what was going to be happening. And by doing that, what we're trying to understand is how fast we can track an object moving across the field of view. So what we have to do is track an object that's moving really, really fast across the field of view. So say we want to do near cam imaging. So we have to make that asteroid look like a star, a fixed target in near cam. And the way we do that is we fix on a guide star with the fine guidance sensor. So this is our fine guiding camera. And we move that star across that sensor's field of view. Does that make sense? So we make a star like this one, track across this field so that an asteroid looks like it's fixed in near cam. Because this is what points and controls the telescope. So by moving the pointing stability fast, it makes the object that's moving look still. So that's what we have to do. Now, just so you gain a little bit of sense of how hard this is, look how big this is compared to how big that is. That means whatever is moving across this field is going to go pretty fast if it's a really fast object, which means we have to find a new star as soon as it tracks off of it, and that takes time. So that's our biggest limitation, is how fast an object moves out of the field of the fine bodies. And so that's why we sort of have, we set out before launch at 30, just because we weren't sure, with JWST being as big as it is, as floppy as it is, how well we could actually point an instrument and make the beautiful images that we want, the same way you see here, by doing that. So we started slow. We tested with some distant asteroid that's moving at a snail's pace, just to see that we can make things move. And then we went faster and faster and faster. When we got to 67, we were like, oh my gosh, this is amazing. We wanted to do a factor of 2 and we're over it. And I was like, hi, JWST. It's a really funny comment, by the way, because I'm a civil servant. For those of you that don't know, that means I'm pretty much a different. It's crazy. Okay, but JWST. Anyway, so when we got to 67, we were like, that's amazing. But then we knew that the DART mission was going to go really fast. The scientist that wanted to observe the DART mission was basically going to do an ambush. So they were going to just point near camp in the sky, in the area where the DART impact was going to happen. Hopefully, the asteroid moved there, impact happened, and then it moved away. So we were just going to sit and stare, and it was just going to smear across the whole field, and we were going to go back and process each individual image. So we were like, wow, we tracked at 67 during commissioning. It's a little bit faster. Let's push the gas a little bit harder. There's no cops around. And so we set out to try to test this, which meant we had to run it on the simulator, which meant we had to find some asteroid that was moving really fast, put that planned trajectory into the simulator, and try to mock an observation and see if it could work. Well, it didn't. And it didn't. And it didn't. And we had to figure out why it wasn't working. And we're getting closer and closer to the DART impact event. I mean, we're talking weeks out now. And then all my colleagues that do my job at the Space Telescope Science Institute that work behind the scenes went on vacation. And so here I am, like, I stand in front of people and I get stickers out. Like, I don't know how to program this. But I have a really smart postdoc that does. So he helped me figure out if we could actually do this. And we worked through with the engineering team. And we finally convinced ourselves that it was going to work, which meant we had to do a test observation. So we had to get that approved and go through all the who's and what's it, which was pretty easy because we're like, NASA mission, we should do this. And they're like, oh, yeah, right. And like Stefanie said, so we listened and we did. So we did our test. We did it at 90 milliarc seconds per second and 110 milliarc seconds per second. And then we couldn't find an asteroid because things were going so fast. And we're like, well, is it bright enough? Do we really know what this asteroid looks like? What's going on? And then my postdoc worked all day, Saturday and Sunday. We had to have the DART observations scheduled following Tuesday. And we worked all day Saturday and Sunday. Finally came back to me and said, found it, nailed it, let's do it. And so we got it scheduled and it was a beautiful success. So it was a lot of overhead. It's not a very efficient way to use the telescope. So we're not going to do 100 routinely, but if there's another DART impact event or an interstellar object or something extreme that we really want to look at that's moving that fast, we'll definitely put the energy into doing it. So we set the speed limit at 75, which is still faster than 50.
What's the difference? All right, I think if we could thank our speaker once more, we will then move on to the observatory.
So I don't have any more JWST stickers, but I do have NASA stickers, and I have JWST postcards. Sorry, all I have. I didn't. Thank you so much again for coming, and thanks to everyone online for joining in, and sorry you didn't get stickers. Oh, I do have a few more. Okay. First come, first serve.
So, yeah, so, are you, I don't know if it's right. Is it raining?
Your best.
Well, I will do this. We will have some, I will go up and one of my grad students or one of the grad students will come up with me. And if you wish to brave the rain from the lobby to the observatory, then feel free to do so. One of our grad students is going to actually VNC into our telescope, and he's going to go through essentially how we work it, what we've done with it, and how the telescope actually operates. So yeah. All right. Let me converse with them for a moment.